Hello everyone, I am Raghu. Welcome back to my channel Chemistry with RK. So firstly, I would like to request, if you are new to the channel, please do subscribe and don't forget to click on the bell icon to get regular updates. So if you can see on the board, so the next concept I'm going to start is stoichiometry, which belongs to junior intermediate. Okay, and now, so you may get a doubt, you may get something into your mind. So I'm going to start stoichiometry by I have taken the periodic table block diagram on the board. So yes, we can able to learn the concept of stoichiometry by using the periodic table. So how it is going to happen? Actually, learning periodic table. Generally, people feel that learning periodic table is a very tough task, and then what I say is, if you can understand the properties, if you can understand the logic behind the placement of these elements in the periodic table, then you will feel chemistry itself is very easy. So what I thought is, better I include the concept of periodic table into the explanation of stoichiometry, so that you can get clarity on both periodic table and also stoichiometry. So let me just start with this. That is, general periodic table has 18 groups. 18 groups are there. So generally we show them with vertical columns. So okay, the vertical columns are called as groups. Generally, these vertical columns are called as groups. And then we have 7 periods. So generally they are shown with horizontal rows. Okay, yes, fine, sir. So 18 groups are there, 7 periods are there, and now those 18 groups are denoted or defined in two particular ways. They are, one is by using Roman numbering, Roman representation, which is very important. The other one is numerical numbering, that is also important, but in most of the cases, we'll be using this Roman numbering in to understand the properties, the bondings, the valencies, the oxidation numbers, which I'm going to teach in the next few minutes. Okay, so try to understand. So what I suggest you to do is, so to remember the group numbers in Roman way, in Roman representation. So Roman representation is very useful to understand so many properties. Okay, so if you can see the first A group elements here: hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. And then second A group elements: beryllium, magnesium, calcium, strontium, barium, radium. Third A group elements: boron, aluminium, gallium, indium, thallium, nihonium. And then fourth A group elements, that is carbon family, the carbon, silicon, germanium, tin, lead, flerovium. Fifth A group elements, nitrogen family, they are also called as picogens. So nitrogen, phosphorus, arsenic, antimony, bismuth, moscovium. Sixth A group elements, oxygen family, chalcogens. So oxygen, sulfur, selenium, tellurium, polonium, livermorium. And then moving to the seventh A group elements, they are called as halogens. And now fluorine, chlorine, bromine, iodine, astatine, tennessine. And then the last zero group elements are inert gases or noble gases or aerogens. So that particular group includes helium, neon, argon, krypton, xenon, radon and oganesson. Let me give you 2 points here before I enter. That is, yes, I bubbled few elements: francium, radium and then polonium. They are radioactive metals. So why did I show particularly, or why did I circle them? Because as far as this particular stoichiometry and the concept of redox reactions is concerned, I am not going to talk about these three elements. Okay, because they are radioactive, so to understand those properties we need to have much more clarity. So which I will be discussing in the separate chapter called as nuclear chemistry. Okay, so we have a separate chapter called as nuclear chemistry, which is only included for advanced. So I will try to post those particular videos of nuclear chemistry in the what do you say that? A few days. Okay, so soon you are going to see most of the videos in my channel. So please, I request you to suggest my channel to your friends, to your relatives, those who are in the people, those who are the students, those who are pursuing from 8th to 12th can easily understand my lectures. Okay. So as far as our discussion is concerned, I am not going to include these radioactive metals into my discussion. And not only these, the elements of 7th period which belongs to P block, which mean neonium, flerovium, moscovium, livermorium, tennessine and afghanistan. Yes, they have discovered and they have given a particular placement in the periodic table, but their properties are yet to be discovered still. Okay, there are so many properties yet to be discovered, so let us not complicate the concept by including them into the discussion. Okay, so yes, you have to remember, because the previous 3 years back, 3 years back they have asked one question from this. That's why I have included these elements into my lecture. That is, moscovium belongs to, okay, so 7th period and then 5th A group. That's the option we need to choose. Maybe in the coming days they may ask, what is the element present in 6th A group of 7th period? That could be livermorium. So for that reason I have included. So try to understand. And now, keeping these things aside, and now just if we talk about these remaining elements. Okay, so as I told you, please try to remember the groups in the Roman representation. That will help you a lot. So how it is going to help us, sir? So if you see group number, especially when I say group number, so I am talking about the Roman numbering. So group number defines about the number of valence electrons. Very important. So what does what is this point mean? Okay, all the first A group elements will have 1 valence electron. All the second A group elements will have 2 valence electrons. Third A group elements 3 valence electrons. Fourth A group elements 4 valence electrons. Fifth A group elements 5 valence electrons. Sixth A group 6 valence electrons. Seventh A group 7 valence electrons, and noble gases 8 valence electrons. And now, okay. So suddenly if I ask you how many valence electrons are present in phosphorus, you must say 5 because it is present in 5th A group. If I ask you strontium, how many valence electrons strontium has? So 2 valence electrons because it is present in 2nd A group. Similarly, fluorine 7 valence electrons because it is located or situated in the 7th A group. Okay. And now the next talking about the period number. So period number is also very important. So period number defines about the valency shell. So what does it mean, sir? If you see potassium is present in 4th period. So its valency shell is going to be 4. If I ask selenium is also present in 4th period. So its valency shell is going to be 4. If I ask you astatine, so in which period it is situated? That is in 6th period. So its valency shell is going to be 6. So here we can understand group number defines about the number of valence electrons, period number defines about the valency shell. And now, once if we know these two terms in detail, if you can understand, I hope you understood these points. And now, once after we get the confirmation, clarity on these 2 points, then we can understand so many things. That is, generally this valency shell or generally shells are represented by N. Okay, so we know that it is principal quantum number. So while writing electronic configuration, generally we generally use NLX method. I hope you know this point. Okay, so please try to understand this. We generally use NLX method to write the electronic configuration. So what does it mean, sir? Suppose if you just see the hydrogen, its atomic number is 1, its electronic configuration we generally write it as 1s1. So what does it mean, sir? If you can see, this 1s1 is in the form of NLX, because this particular, the number which we are writing in front of the subshell is nothing but the principal quantum number, and L defines the subshell here, subshell, that is S, and now here X defines the number of electrons. Clear? So this N defines the shell number or valency shell number. Okay, so, or let me just write down. Yes, N is the principal quantum number. And now when it comes to L, so L is going to be our azimuthal quantum number. And now X is our number of electrons. Okay. So we know that principal quantum number starts from 1 and it goes to infinity. And then when it comes to azimuthal quantum number, it starts with L equal to 0, which is going to be our S subshell. L is 1 for P subshell, L is 2 for D subshell, L is 3 for F subshell. Clear? And now by using this NLX method, we can able to write down the electronic configuration. So how, sir? So simple. If you observe, everyone observe here. So potassium is present in 4th period. So we can write its valency shell is 4, and it is present in S block. Okay, it's present in S block. So we can write down S. And now it is located in first A group. So we can write down it is 1. So this 4s1 is the valency shell electronic configuration of the element potassium. Clear? So let me just you try to just take a screenshot. Okay, and then next let us continue. So please, you have to remember these 2 points, very important. By taking the help of these 2 points, we are going to do so many miracles in the coming lectures, coming chapters even. So I request everyone, those who are watching this to understand everything, so that the next coming lectures you will feel very easy. Okay, so by using the previous concepts, so let us write the electronic configuration for hydrogen, and let us move with this. The sodium's atomic number is 11, potassium it is 19, and then rubidium it is 37, and then cesium it is 55, and then francium the atomic number is 87. So now principal quantum number is N, azimuthal quantum number is L, and then X defines the number of electrons. And now by using this concept, you can write down hydrogen's atomic number is 1, it is present in first period, S block, and then it belongs to first A. So we can write down as first period, S block, and then first A group. So the hydrogen's electronic configuration is 1s1. Next, moving to lithium. So lithium, actually we can write down that is helium, second period, it is present in second period, and then S block, and then first A group. Similarly, sodium will be neon, third period, S block, first A group. Similarly, we can write down the electronic configurations for most of the elements by using the same logic. So that is krypton. Okay, so that is 5th period, S block, and then first A group, and then krypton, xenon, 6s1. Similarly, radon, 7s1. So if you can see, by taking the help of group number, period number, we can easily write down the electronic configurations. So, and now if you just observe carefully, so these are the electronic configurations of all these elements. Among these electronic configuration, the last outermost electronic configuration. So if we try to write down the general electronic configuration for the first A group elements, so what is the changing factor here? That is, S1. So anyway, they all belongs to first A group, they all are presenting S block. So S and 1, they are constant, but only difference is we get in the case of principal quantum number. So generally we define or denote this with N. So the general electronic configuration of first A group elements are NS1. Okay, it's not only this, we can able to write down electronic configurations of any elements by taking the group number and period number concept. So if I ask you randomly magnesium, okay, if I ask you magnesium, its atomic number is generally 12. So if I ask its electronic configuration, so that could be neon, and then it is present in second period, S block, and then second group. That's it. Okay. So this is the preceding noble gas. We need to go with the preceding noble gas. And then if we move with the beryllium is top on the magnesium. So the configuration is going to be helium and then 3s2 actually. Magnesium is present in third period, so this is going to be 3s2. And then beryllium second period s block and then 2s2. Similarly, next if we move to magnesium calcium, so it is going to be argon 18 and then fourth period s block and then second A group. That's it, 4s2. So likewise we can write down the electronic configurations of complete second A group elements. And now if we observe the outermost electronic configurations of all the second A group elements, they are going to be 2s2, 3s2, 4s2. The overall general electronic configuration of the second A group elements is going to be ns2. Hope you understood. And now by comparing the first A group electronic configuration, second A group electronic configuration, we can able to write down the general outermost electronic configuration of the entire S block. That is going to come out as, so what is the difference you see here? For first A group it is ns1, for second A group it is ns2. So both together we can write for the entire S block, the electronic configuration is going to be ns1 to 2. So this is the general outer electronic configuration for entire S block elements. So ns1 for first A group, ns2 for second A group elements. Clear? So likewise we can write down the electronic configurations for any of the elements. Okay, so you please try to take the screenshot. Okay, next let us write down for third A group elements. Okay, especially that is for boron. If we try to write down, that is going to come out as helium, that is second period. So it is 2s2, 2p1. So why p has come into the picture now? Okay. So actually boron is present in p block, and now since S can accommodate maximum of 2 electrons, so obviously one more electron will be left. So that must enter into 2p. So we can say that is helium 2s2, 2p1. Okay, and then similarly if you try to write down for aluminium, that will be coming out as 3s2, 3p1, 4s2, 4p1, 5s2, 5p1, 6s2, 6p1, for nihonium 7s2, 7p1. So overall for the entire third A group elements, if we try to write down the general electronic configuration, it is going to come out as ns2, np1. Hope it is clear. And then similarly, if we try to write down for fourth A, it is going to come out as ns2, np2. For fifth A, ns2, np3. For 6th A, it is ns2, np4. For 7th A, it is going to come out as ns2, np5. For noble gases, we are going to get ns2, np6. Based upon this particular elements, we are going to define the stability, because they have 8 electrons in their valency shell, and the property is called as octet. So having 8 electrons in the valency shell gives more stability to the elements. I'll come to this octet soon. Okay, so by observing all these general electronic configurations of third A to noble gases, we can able to write down the general electronic configuration of the entire P block elements is going to be ns2, np 1 to 6. Okay, and now next let's think about these elements. Since I told you these noble gases are the ultimate stable elements in the periodic table, because they have octet configuration in their valency shell. Yeah, they have 8 electrons in their valency shell, so they are considered as more stable. And now, like noble gases, even the other elements also will be interested to become stable. Like how we want to become more stable in our own life, then elements also will be interested to become more stable like the noble gases, because no one will be interested to be like a slave in in front of someone. So obviously we want to become stable, even they want to become stable. And now in order to become stable, they have some particular criteria to consider. That is, all the 7th A group elements, if you see, they have only 7 valence electrons, and now they are in requirement of 1 valence electron to get octet. Is it right or wrong? And then somehow, if the 7th A group elements are going to get 1 electron from somewhere, they are going to get the octet configuration, so that they will also become stable. So in that particular competition, they will be in search of 1 electron. Similarly, when it moves to 6th A group elements, they have 6 electrons, and now they will be in search of 2 electrons. If someone can give 2 electrons to the 6th A group elements, they are going to get more stable. And now slowly in this particular angle, they are going to play individual politics, so that oxygen will be requesting the opponent elements to give 2 electrons. But why some element will give 2 electrons? Why some element will give 3 electrons? Actually, to understand that, let us understand the nature of elements. Okay, so we have actually 3 types of elements. Okay, generally elements are classified into 3 types. They are metals, and they are non-metals, and they are metalloids. Yes, okay. And now what does it mean? So what type of nature metals, non-metals and metalloids are going to show? So metals generally have a tendency to lose electrons. And then non-metals will have a tendency to gain electrons. And now when it comes to metalloids will be having, the properties of metalloids will be in between metalloids and non-metals. Or metalloids will show, metallic and non-metallic characteristics. Okay, so depending upon the situation, the metalloid can able to either lose, or it can also gain the electrons. Yes, this is possible. And now here non-metals have a tendency to gain, metals have a tendency to lose. And now fluorine want 1 electron, lithium is ready to give 1 electron. Why lithium is giving 1 electron here? Just going back to our concept of electronic configuration, its electronic configuration is actually helium 2s1. Yes. And now I hope you understood. If this lithium is going to lose this 2s electron, then it is going to get helium configuration with 2s0. Now second shell, s subshell, have no electrons, so then we can assume that particular subshell is not having any physical significance. So this particular lithium is going to become, as I told you, lithium by losing 1 electron, it is going to get plus charge. So what does it mean? Lithium will be very interested to lose 1 electron so that it gets the preceding noble gas configuration. And now that 1 electron will be readily taken by the 7th A group elements. Yes, there comes the friendship in between 1st A group elements and the 7th A group elements. There starts a kind of interest in between 1st A and 7th A. Okay, and there starts the mutual understanding, and now the elements will mutually go and interact with each other. And now fluorine will go to sodium and request, sodium, please give me 1 electron. And then yes, sodium will ask, why would I give 1 electron? And then fluorine will try to explain, if you can lose 1 electron, then you get the preceding neon gas configuration, and that electron will be, I will take that particular electron and even I will also get stable. So this is the mutual understanding the elements are going to generate among themselves. So keeping this point in mind, the entire elements are going to undergo losing and gaining electrons process. So what type of elements generally lose electrons? Metals. So I have shown the metals in the blue marker with the blue marker, and then non-metals with the green marker, and then metalloids with the red marker. Yes, and now I hope you understood why I have taken periodic table here to explain the stoichiometry. Soon you will understand in a better way. So let me just go with this. Since fluorine have 7 valence electrons, that too it is a non-metal. So non-metal have a tendency to gain electron. Now fluorine gains 1 electron and then it gets -1 charge. And then not only fluorine, all chlorine, bromine, iodine will be gaining 1 electron. They are going to get -1 charge. So non-metals will gain electrons and gets negatively charged. Okay, and then similarly if you come to lithium, so lithium will try to lose 1 electron and gets positive. We know, I already told you, metals generally loses electrons and they get a positive charge. How many electrons they are going to lose depend upon its group number. How many electrons it is going to gain depend upon the group number. That's why I told you to remember the group number. And now okay, and then next moving to the 68 group elements, oxygen non-metal, so it is going to gain 2 electrons, sulfur non-metal. So likewise we can able to write down simply the charges. And now if you see this beryllium +2, magnesium +2, calcium +2, strontium +2, barium +2. Not only particular element, all the second A group metals are going to get +2 charge by losing 2 electrons. Those 2 electrons will be readily grabbed by either any of the 2 elements of 7th A or 1 element of 6th A. Hope you understood. Because one particular second A group element is going to lose 2 electrons. Those 2 electrons will be taken by one of the 6th A group element or 2 elements of a 7th A group element. Okay, and then next moving to the third A group metals, aluminium +3, gallium +3, indium +3, thallium +3. As I told you, I am not going to include these elements into my lecture. Okay. Similarly, tin 4th A group, so it will lose 4 electrons. Actually, tin and lead will show different charges also. Okay, based upon something called as inert pair effect. So inert pair effect will be clearly explained in the 3rd A and 4th A group elements. When I start boron family and carbon family, I will try to give you more explanation for inert pair effect. So actually inert pair effect is reluctance of NS pair of electrons to take part in bond formation. Okay, so you will not understand that inert pair effect now. So let me just skip that for time being, and then I'll try to discuss this inert pair effect in the boron and carbon families. Okay, yes. And now keeping this point again, bismuth also shows +3 according to inert pair effect. And now moving to the nitrogen non-metal 5th A group, it has 5, so it wants 3. So phosphorus also, and then carbon. When it comes to carbon actually it is present in 4th A, so it may lose. Actually carbon it is present in 4th A, so we generally think that it is having 4 valence electrons. It wants 4, and now is there anyone ready to give 4? No. Is there anyone ready to take? Actually for taking someone will be ready, but for giving no one will be ready. Okay, so keeping this point in mind, carbon rather forming -4 or +4, it is going to get octet by sharing the electrons. That we will discuss clearly when it comes to the bonding and then sharing and then transfer of electrons. That we will discuss clearly in chemical bonding. Okay, but as of now, so I hope you understood how I am writing the charges. Why nitrogen need to have -3? Because it is present in 5th A group, so it has 5 valence electrons, so it need 3 more valence electrons to get octet, so obviously it will take from someone, so it gets -3. So the positive and negative charges on elements depends upon the number of electrons they are going to lose or the number of electrons they are going to gain. When it comes to metalloids, just now you can see here metalloids can able to lose or gain. So keeping that point in mind, so boron can have ±3, silicon can have ±4, germanium can have ±4, and then arsenic will have ±3, antimony will have ±3, here ±2, here ±1. Why ±1? I hope you understood. When the metalloid is showing most of the metallic characteristics, then it will have positive charge. When the metalloid is showing most of the non-metallic characteristics, it is going to show negative charge. Okay, and now I gave almost charges for all the elements. I didn't give for hydrogen. Let us now talk about that. Hydrogen actually have two charges. The possible charges for hydrogen is two charges, +1 and -1. Okay, so when do hydrogen shows +1 and when do hydrogen shows -1? When the hydrogen is combined with any of the non-metals, then hydrogen is going to show +1. When hydrogen is going to combine with any of the metals, then hydrogen is going to show -1. Why, sir? Because when hydrogen, suppose let's say, when hydrogen want to combine with, suppose let's say, lithium has only one choice, that is to have +1. In such case, this hydrogen will have -1. Here, fluorine, suppose let's say, fluorine has only choice to have -1. In such case, hydrogen will take +1. So depending upon the opponent element, the hydrogen is going to have +1 or -1. Sir, why +1? So what do you mean by +1? Hydrogen have actually one electron and that electron also being loosed. And now what does it mean? Why the hydrogen is losing electron? Actually hydrogen is not interested to lose, but the opponent element is so strong to pull the electron. That is like fluorine. So fluorine is more electronegative, so it has more power to pull the electron from any one of the elements. So in that particular aspect, in that particular situation, hydrogen have to give out the electron to fluorine. So fluorine will forcefully take the electron. When it comes to here, lithium. And now actually hydrogen has 1s1 configuration. So if hydrogen can also get one electron from somewhere, then it is going to get helium configuration. And now who is ready to give that electron? Lithium is going to give that one electron, and that so that the hydrogen will take that electron and it will convert it to H-. Clear? How interesting the chemistry is now. Okay, so this is how the charges being given for different elements. And now the noble gases have no charge because, I hope you know, because they are already stable, they don't want to either lose or they don't require any electrons. Okay, so since they have octet configuration, no need to think about their stability because they are already stable. In such case, the remaining elements are now in a competition to get more stable like noble gases. Okay, and now these charges I am going to give some name called as oxidation number. So for this reason, I have taken the help of periodic table. What, sir? What is oxidation number? And then so far it is very nice, and now you are using a term called as oxidation number. Actually, the charges you can see here on the elements are taken as the oxidation number of that particular element. What does it mean, sir? If I ask you what is the oxidation number of fluorine, we generally take it as -1. What is the oxidation number of oxygen? We generally take it as -2. Make a note, please. Here, oxygen have more than one oxidation number. That is, apart from this -2, it has some other oxidation numbers also that I will discuss in the next video. Don't worry, okay? And then next, if we come to lithium, lithium has only one +1 charge. There is no other possible oxidation number. So generally for metals, they do have only one type of oxidation number or charge, except these transition elements. The few transition elements show more than one positive charge. So that particular factor is called as variable charges. So if you see, even this tin will have, other than +4, it will also show +2 also. Even lead also, apart from this +4, it will also show +2. So that we will discuss maybe after within the next 5 minutes. So just keeping this particular concept in mind, this is how we are going to give the charges, and those charges we are going to use in terms of oxidation number calculations. So if I ask you what is the oxidation number of calcium, then you must remember +2, sir. Why? It is a second A group metal. Metals loses electrons. How many electrons it is going to lose? 2 electrons, because it is present in second A group. Similarly, aluminium, yes, the oxidation number of aluminium is +3. because it is present in third A group, and that too it is a metal. So likewise we have to remember them. Okay, and now these particular oxidation numbers we are going to use in the calculation of oxidation numbers in the coming video. Thank you so much. And please, I request everyone, those who are new to the channel, please do subscribe. I am going to include very interesting videos in the coming lectures. I am going to upload maximum videos as soon as possible, and I invite all your requests. Like in case if you want a particular concept to be discussed, you please post it in the comment section. I will try to post it as soon as possible. Thank you so much. See you soon.